Well, we made it, folks. It's now week 7 out of the 16-week semester, and we're nearly done with chapter 14. We just have that last example that we didn't want to try to race through before we went to weekend last week. And finally, on the Moodle website is the chapter 15 notes. This is kind of an infamous section, but it's also a really important section. So we'll take our time with that. And after we're done with chapter 15, we'll move into chapter 17, doing the ordinary statistical methods, the ones that are well supported, don't have any logical issues like we saw in chapter 14. So that means we're going to do the exciting work of plugging all those holes that we found in that particular section. But not too many announcements for today. Any other questions or comments, folks, to start us out? Okay, well, let's jump in. For chapter 14, here's where we left off, example 6, but it was a long weekend. I think I say this each and every time, so let's kind of refresh what we did for our final problem. We are running a top to bottom hypothesis test on this fictitious example that we can imagine being pretty realistic in certain situations. They provide us with nothing but the sample mean, a sample size, a population standard deviation, and a significance level alpha. From that, we wrote out what the parameter would be. We found the hypothesized value is 5.2. We've dropped 5.2 into the null and alternative hypothesis. And the reason we knew that that was the value to be tested, we often call that mu naught, it's only because it came from the major question that was being posed in the problem itself. Oftentimes, this being the research question is really just stating the alternative hypothesis in ordinary words. And it was our job to just write it down symbolically like that. At significance level alpha is 0.05. Next thing we did was check conditions, run through the formula. This is just an ordinary z-score formula. We took the sample mean, the mean of the population subtracted from it, from the null hypothesis, and we found that the data in X bar has a distance away from the claim in H naught, the mu naught value here, which is 5.2, a distance of over 2 standard deviations. When we measured that as a p-value, really all we had to say is p norm z, which is kind of convenient. The p-value is 0.0217, less than the significance level alpha. And so we were allowed to say we have significant statistical evidence. The mean dissolved oxygen count is less than 5.2 parts per million. Then we mentioned some things that could challenge that conclusion as well. What happened there? That was weird. That's just not a spot to scroll to, I guess. And that's where we left off before going off to the weekend. Any questions, folks, about that quick rundown? Yeah. Only from the very beginning. You're on the right track. Yeah. We want to try to prove that we'll either reject or fail to reject. Absolutely. I'm glad you asked that question because, this was a very specific outcome. Natural question is, what if this right here came out different? Let me see if I can copy that. Let's call this just an additional remark. I put a little break here just to say the problem ended, but there's more to discuss on this. So let's paste that in. And for the remark, let's say, suppose that the p-value was not 0.0217. Let's change this in a major way, 0.0517. The inequality here is now incorrect. We have strictly greater than. You could say greater than or equals, because this is when we would fail to reject, but it just seems kind of strange to write that in, honestly. I think a lot of people would put in just greater than, which means we will fail to reject H naught. And this is kind of tricky in a way. For a large p-value, it does not mean we're accepting that null hypothesis as true whatsoever. It just means we lacked the evidence against it. Doesn't prove its truth. We just don't have any evidence to prove its falsity. So our conclusion now runs this way. Recall up here, we can't accept H naught as true in our conclusion. So if we're in this outcome with a large p-value at size alpha or larger, we fail to reject H naught is how the conclusion gets written in. We can never say we have evidence that H naught is true. At best, you could say our data is consistent with the statement in the null hypothesis, but that's a dangerous conclusion because people could misconstrue you as saying we have evidence the null hypothesis is true, which isn't the case either. So let's write this out. Imagine we did have this large p-value. We can say then our conclusion is this study failed, lots of ways you could word this. I'm going to say failed to provide significant statistical evidence that, here's the tedious part one more time, population mean dissolved oxygen count in parts per million downstream. I'll just paraphrase this even further and call it simply just downstream of the plant being implied. We didn't find any evidence that it is less than 5.2. I guess we said parts per million once, but I'll just restate it here. So for a large p-value, notice our conclusions look about the same. Well, you're either saying we have significant evidence that the dissolved oxygen count on average is less than 5.2, or we say we failed to find that statistical evidence. So the failure here was only because of the greater than direction. If it was exactly 0.5, we would still have a failure as well. But any questions at all, folks, with that second kind of conclusion? Okay, I think these conclusions definitely are kind of tricky. This is the one where we found the evidence. This is the one where we did find the evidence. Sure, it's always just organized by how your p-value relates to the significance level alpha, but it didn't quite resolve why can't we accept H naught as true in our conclusion. If we can't really say exactly what the problem is there, this kind of stuff is always just kind of vague. So example 6 is our attempt to try to plug in that logical loophole, well, not really a loophole, but that logical problem of what's going on with H naught. And there's a couple arguments you can give here. One argument that I often say, just as a quick way to explain this, is if the very first step in conducting your hypothesis test is to assume H naught is true so that you can measure a test statistic and compute a p-value, then concluding H naught is true could never be done. That'd be entirely circular logic, right? Assuming something is true and then concluding it's true at the very end. That will never work logically. But a better way to think about this is absence of evidence against H naught. This is having a large p-value. We can't reject H naught, so we have an absence of evidence against it. But absence of evidence against H naught is not evidence H naught is true. So in other words, you cannot prove H naught is true by just failing to find any evidence against it. This is a huge logical loophole as well. Carl Sagan himself said it once, he's a famous astronomer, absence of evidence is not evidence of absence, but he is not the first one to come up with this idea. This is an old logical argument over 1,000 years old from ancient philosophers. And we borrowed it again for the logic of the actual proceedings of our court of law. So this is the problem right here. And another way to say this is the only way to prove H naught is true is not to do the inferential statistics we've been doing whatsoever. You can't take a sample. You have to take a census of the population and once you have a census of the population, your sample is the whole population, in other words, we can compute mu at this point. We'll compute the population average because we have access to the entire population. And then we just check the value of mu against the statement in H naught. It's either true or false now. So the only way to prove this, take a census from the population and directly compute mu. If it's exactly the value in the statement of the null hypothesis, probably really unlikely. But if that happened, then yeah, we have proven H naught is true. Notice how terrible that is, and in a lot of cases impossible. The US government itself attempts a census, and it's debatable what the accuracy is, even for that enormous, expensive undertaking that we're required to do by the Constitution itself. So censuses are not easy, populations are tricky once we try to do them. And in the right context, if you take a census of a population, you might have destroyed that entire population at the same time. So who cares what happens with mu naught any longer if that population is gone from existence? So there's actually a lot of trouble with hypothesis testing. And part B, well, at least one thing we can say here is the p-value is never the probability that H naught is true, so that helps us out. We can now say what is the correct interpretation of p-value once and for all right here. Again, p-values are tricky themselves. We want to think of what is the process of conducting a p-value or computing one. You immediately assume that null hypothesis is true. And so this is the setup for the right, let's put in here an extra word. It's not a practical interpretation. Our practical interpretation are these conclusions that we're giving. And we never said probabilistically what that probability even represented. We just said, what is our conclusion relative to the p-value against alpha? But if we want to interpret the p-value, not even the probability H naught is true, here's how the interpretation goes. We will test H naught, mu equals mu A, or excuse me, mu 0 for mu naught, against, it can be any alternative, but so we don't write down 3 equivalent statements, I'll just write down the default test. HA, mu naught equal to mu naught. So when we go to test this out, we compute Z, which is going to be X bar minus mu divided by sigma over the root n. And from there, we calculate a p-value out of this. The p-value is going to be, this is a two-tailed test, so see the guide above for a quick reference. 2 times probability that Z, uppercase Z, is bigger than lowercase z, where uppercase Z is distributed N01, standard normal distribution. So this is the overview of what we're doing when we're conducting a hypothesis test. And the p-value is going to be equal to the probability of obtaining a sample mean of X bar, the same sample mean that it was discussed right here in the test statistic. So it's a probability of obtaining a sample mean of X bar. Actually, let me reword this just a touch. Sample mean as extreme as X bar. or more extreme. By X bar being an extreme statistic, we mean it's far away from mu naught at some value, and we want to find the probability that it takes this value, or more extreme, even further away from mu naught, whatever that value is in the null hypothesis. So the probability of obtaining X bar as a data as extreme as X bar or more extreme under the assumption H naught mu equals mu naught is true. So that's directly what that probability calculates. And it's a pretty wild probability for sure. This is what we're getting all together. So every p-value we compute is just telling us the probability of getting our data as far away from the statement of the null hypothesis as what we found, or even further away. So that computes our p-value. Well, that's kind of a technical discussion, and now we see why we don't mention the probability necessarily if we're giving a practical interpretation. These are the details we would have to give if people want to explain why did we reject the null hypothesis, what did the p-value represent. This would be the explanation. Well, at that case, we did it, folks. This is the end of chapter 14. Confidence intervals and hypothesis tests feel wildly different, but always remember, in a very, very real sense, the two-tailed test here that's indicated, whatever conclusions it gives, is the same conclusions that our ordinary confidence interval would give as well. So even though the methods feel very different, they're really trying to do the same thing. One just gives you a conclusion, hypothesis tests. The confidence interval also gives you the estimate after you've made the conclusion. But at this point, we can save this up and now move over to chapter 15. Any last questions, comments, or otherwise, folks, before the next chapter? It's working hard on this. Let's hope it responds at some point. There it goes. Okay, off to chapter 15 then. The computer is really slow today. There it goes. So our goal here in this study, or excuse me, in this chapter, is to think a little bit more about, let's suppose that you really are a researcher, maybe biology, chemistry, physics, engineering, and you've landed a huge government contract. Before you even conduct any experiments, collect any data, there's always a planning phase. And so that's kind of the purpose of chapter 15. Planning that your sample size is large enough so that when you go to conduct a confidence interval analysis, the margin of error hits a certain target. Or even more nasty in a certain sense is with hypothesis test, determining if your sample size is large enough so that the power of the test is in a targeted range. So the power of the test is the hard concept in this section because it deals with the significance level alpha, a new definition we haven't hit, effect size, and it gives us this as a probability. The power is the probability of correctly rejecting the null hypothesis under the assumption a specific alternative hypothesis is actually true. So the power of the test is something we're going to compute just to get a feel for how these go. Before we do all that, though, the dual concept for confidence intervals is margin of error. Think of margin of error as the same idea as power of a test in a certain sense. Well, let's begin the notes in earnest. For a confidence interval analysis, we come up with a confidence level C. It's usually a lot of thought goes into determining that level of confidence. And it'll be for a population mean mu. We'll do other confidence intervals for different parameters, but for the moment, that's what we have. However, it's interesting to know all the confidence intervals we give have this feature. It's a point estimate of whatever the parameter is. Our point estimate for mu is X bar. Then we add and subtract a margin of error. This is the error in estimating mu approximately X bar. Margin of error helps us know how accurate that estimate was in the first place relative to this confidence level stated earlier. Margin of error is just going to be critical number Z star multiplied by sigma over the square root of n. So that's how it all goes together so far. So the margin of error is this part right here. Sigma, again, is a value that is defined to be the true population standard deviation. Well, this formula gets used a lot, and oftentimes we have no idea what sigma is. If we're going to use this kind of formula to determine sample size required for a margin of error m, we need a value for sigma. Oftentimes we could go to historical data, make some kind of estimate. And if we're going to estimate that way, if we have to estimate, we estimate high, because we want to give a conservative estimate. Once we get our confidence interval, we really want to get the right level of confidence by targeting the margin of error just right. So we'll allow our sample size to be a little bit higher through this, estimating a little bit higher on sigma if we are making those kinds of estimates. So these are the conservative estimates we would make in this situation. Example 1 just says, find the sample size required to obtain the margin of error m. Okay, let's do that. First thing we do is we just grab the formula for the margin of error, m equals z star times sigma over root of n. This problem is all about getting the sample size, so our goal is to solve for n right there. We can multiply both sides by square root of n, divide both sides by m, and get the new equation, square root n equals z star sigma divide by m. Next, now that we have the square root of n isolated, just square both sides of this equation. This will then require or imply the sample size n equals critical number z star multiplied by sigma divide by the margin of error m, square that whole result, and we've got the sample size. But we need to be careful with that sample size because this is probably not an integer. In a lot of problems, this may be 50.72, something like that. Just like we estimate high here, so the sample size is large enough to really hit the margin of error, we want to estimate large here as well for a conservative estimate. So when we use this formula, round up to the next integer would be the standard estimate once we get this value here. So if this was like a 5-point question and you just gave me like 32.7, you might lose 1 point, no big deal. We should really say the sample size is 33 though, estimate a little bit higher, so that once we collect all of our data, we'll have the right targeted margin of error. Well, any questions, folks, with the, I guess this is a derivation on this one, coming up with that formula? Okay, next thing we want to do just immediately is work with this formula. This is kind of nice in a way. I mean, if you're doing a confidence interval analysis, you want to have a certain level of confidence, but you don't want your interval to be so wide as to be useless. You want to narrow it down so that the estimate you get is practical. So we target the sample size n here to make sure that margin of error is controlled and not just completely out of spec. So let's try this out on example 2. This one looks like it has something to do with the Olympics or something along those lines. A lot of elite athletes on this problem. We're told that the distribution of total blood cholesterol level in the population of young men aged 20 to 34 years is close to normal. That's good information. Standard deviation at 4.1 milligrams per deciliter. Usually don't want to get the unit right if you're talking about a bodily thing like blood cholesterol. We're told next a cholesterol level less than 200 milligrams per deciliter. It's recommended for adults. Don't take that as medical advice. It's just typed out verbatim from the textbook. And we're considering a study where you plan to measure the blood cholesterol level for cross-country runners to determine if they are in the healthy range. So we have information for population of young men in that age range. And we're told that the cholesterol level below 200 is recommended for all adults. Perhaps are referring to these people here. And now we're going to a whole new population, well, I don't know how elite they are, but let's imagine elite athletes, cross-country runners. Biology or metabolism for these people as elite athletes may not be in spec with the general population, so we may want to estimate that to see how different it could be. The question then is, what sample size will be required? So now the sample size is the unknown. We haven't even collected data on this. We're just planning to estimate the blood cholesterol levels of cross-country runners with a margin of error equal to 5 milligrams per deciliter. So there's our margin of error statement. And let me change around my color coding real quick here. We'll do that at 90% confidence. So those are the elements. Next thing we'll do is just drop in the formula and put in the values we need. So N will be Z star times sigma, divide by M and square it. So this computation is actually pretty fast, but there's some stuff here that's missing. For example, I don't know Z star, but we do know the confidence level. We can go to RStudio to compute that really rapidly, or just go to the chapter 14, cite the table. That's so fast to compute, it's almost a waste of time to go look it up again. Let's just go confidence at 0.90. And while we're at it, why not just include sigma, 41. Margin of error, we usually just denote with a variable m, is 5. Then once we have all that, the last thing we need is the critical number, Z star. Z star gets, our syntax that we left in the chapter 14 notes was Q norm. 1 minus C divided by 2. So this is getting the area in just one tail, the left tail. In order to force Z star positive, we could set lower dot tail as false. But you always have to question to yourself, does it matter if Z star is negative? Not in the confidence interval formula, and not even here, because power 2 is just going to wipe out a negative sign. But it's still weird to cite a negative Z star, so let's go lower dot tail, set false. Run all this, and, well, Z star is now that figure right below here, 1.6449 if we're rounding. So I want to do this in kind of two ways. Let's do it by hand to show what you would do if you were just plugging this into a calculator. Then I'll just share the script right here if you want to do it in a slightly more rapid way. So over here in this approach, we'll plug in 1.6449. It multiplies against this value right here, sigma. So drop in your sigma value, 41. We divide that by the stated margin of error, 5 milligrams per deciliter. I'll just throw in a 5 there. Square the whole thing. And that'll do the job for us. We could retype this all into the calculator below, or honestly, it's not a bad idea just to say sample size is going to be this structure. Or let's put it in this way. Z star that we've defined times, we never specified sigma, so let's just throw it in. Sigma was 41. So Z star times sigma divide by margin of error m raised to power 2 gives us, run the whole thing, sample size at 181.9207. I'll write it this way, 181.9. But a good call, absolutely. We can't report that figure, but like you said, it informs us we'll use a sample size of 182 in this problem. So let's say down below, we will use n equals 182. And that could be a problem. At 182, that's a lot of elite cross-country runners, Depending on how elite these are, maybe we're looking into a specific country like Russia or something along those lines. If these are a small pool of Olympic athletes, there might not be 182 of them. Some of these populations we deal with are very, very small. So this informs us study might not be able to be done as planned. So this is good information already. Maybe we have to be a little bit weaker on this and accept a wider margin of error. We did that to make the margin of error 10. Notice the savings here. We're down to a sample size of 45. All we did was we halved the margin of error, and it is greatly reduced, about quartered, the sample size required. Kind of strange in a way. But let me return the syntax back to its normal form. Any questions at all, folks, coming up with that sample size? Okay, well, if you decide to use this syntax, you would have to change all of that information. Then down below, Z star is just kind of separated to indicate it's not something that you change, and that's what would be outputted. So in a really nice way, this solves the problem once and for all. You can just reuse this, change some values around, and you'll be all set. Any questions at all, Ben? Yeah, go ahead.
Just to clarify, so for rounding up, does that mean if you get, say, 181.3 to round up to 182, even in that situation, or is it, or you round to 181?
I would say we would even round up in that situation, absolutely. If we had, say, 181.003, you know, at that point, it's kind of a borderline situation. And rounding down for that would probably be very good judgment. But for most cases, we would definitely be rounding up even at a 0.3 right there as well. Other questions so far? Okay, well, this is kind of nice. Half the notes are done. This is planning a study, dealing with confidence intervals. Now, if we're going to plan a study and we want a hypothesis test, it goes a little bit different. We have to be a bit careful with this. There's lots of stuff to say out of nowhere. So keep in mind what we did right here, coming up with the sample size required, 182, to target a specific margin of error, 5 milligrams per deciliter, is not too different than coming up with the sample size that hits a specific power for the test. Oftentimes we want power to be really high if possible, around 99%, maybe 95%. Depending on how high the stakes are, maybe even more, 99.9% might be the requirement, depending on context. But there's really a lot to say here, so let's work through this carefully and slowly. Some of these objects we've seen before, like the significance level alpha. But another way to view alpha, here's our author's words, is it's answering the question of how much protection we want against getting a statistically significant result, rejecting the hypothesis, when there's really no effect in the population. The null hypothesis was essentially true, in other words. And typical values are the 0.01, 0.05, 0.10. So how does alpha get involved? Well, when we make a hypothesis test and perform a conclusion, there is now a two-way table of all the possibilities that can happen. If you reject H naught, you either made the right choice or you made a mistake. What I mean by mistake is, I don't mean a statistical mistake. I mean, the sample data that you got just happened to be weird, random sampling being an issue there, and gave you the conclusion contrary to what should have been happening in the population. So that can happen even if you do your statistics flawlessly. So if we reject H naught, but the null hypothesis was essentially true, we will call that a type 1 error. And already this is kind of crazy. When we set the significance level alpha, it is the literal exact probability of the type 1 error. That alone deserves some explanation and some description because that's a really abstract thing to say out of nowhere. Moving over to the next line though, if we reject the null hypothesis and some other thing was true, the alternative hypothesis, we made the correct decision. So that's what's going on right here. But you might have noticed something is really be kind of weird with my alternative hypothesis right here. We have said, well, not often, but we have said in chapter 14, When you form an alternative hypothesis, you need either strictly less than, strictly greater than, or not equals. You never have all quality in the alternative hypothesis, unless your goal is to compute the power of a test. In that case, you actually need a specific hypothesis right here. Where does mu A come from? It comes from the effect size. The effect size is going to inform us on how to actually calculate power, or how to actually calculate the probability of a type 2 error, which is wildly more complicated out of nowhere. Probability of a type 1 error is specified by you when you form your hypotheses. Type 2 error doesn't quite go like that. So what we do is we decide how large of an effect in the population is important in practice. Hold this thought already right here. We've kind of considered effect size when we go up here and say, we want to be informed by the sample size required for this margin of error. It would mean the experts would say, anything less than 5 milligrams per deciliter is so small to be of no practical importance whatsoever. That's the effective size most important to them. So that's kind of what we were doing with confidence intervals. And down below here, we don't say this effect size necessarily when we form our hypotheses. This is something that will have to be extra information when we're just doing the whole planning phase of testing hypotheses. So the effect size is defined to be the distance between mu naught, statement of your null hypothesis, and some value mu A. That's the mu A you see down here in this specific alternative hypothesis. It's one of infinitely many possibilities coming from the not equals, but we need a value set equal to actually compute power. So that's why I always call this one a specific alternative hypothesis. It's really very weird. In order to get any of these values like power, probability of type 2 error, you literally do need a number there. So mu A is found from setting a fixed value. In the alternative, mu equals mu A. So we decide how small should this be, find the value mu A, and plug it in. And we'll do exactly those steps in context with the problem just down below here in the notes to make this all a little bit less vague. But finally, after we've done all that, we can calculate power. Power is just a complement of this. So whatever beta is, we can say power equals 1 minus beta, the ordinary complement rule from probability. In our author's words, power answers the question of how confident do we want to be that our study will detect an effect size, say, that specific alternative that we think is important. So correctly rejecting the null hypothesis under the assumption a specific alternative is true, which is formed by considering the effect size in the actual statistical problems context. Lots of stuff to say, so that's why we're going to spend some time with this and break down each one of these things. First things we want to do is redefine what we mean by probability type 1 error, probability type 2 error, because if we can say exactly what those are, then we'll be in great shape. But let's consider a couple more statements. Probability of type 1 error is alpha, like we mentioned, and the value alpha has to be carefully chosen. Because what we're really trying to do when we set up a statement of competing hypotheses is we're balancing the direness of making a type 1 mistake versus how bad is it to make a type 2 mistake. If we can balance both of them simultaneously, then we're planning the study in a well sense. So to reduce type 1 error, just make alpha smaller and you're all set. But there's a bit of a fight here. If you set alpha to smaller values, your probability of type 2 error goes up. So you have to consider that as you're making alpha go down. That might be appropriate. If type 1 error is very devastating as a conclusion to make, then we should make it small, but now we're inflating type 2 error. So that's just something we have to live by. In order to reduce type 2 error, if type 2 error is worse, we set alpha to larger values, maybe a 0.10, for example. This has increased the probability of a type 1 error. And so again, there's a balance between the two. That's basically a literal fight between which error are we trying to avoid the most. Think of it from a corpus standpoint. You might think along the lines of, would we be sued for the most money? Where are we most liable, in type 1 or type 2? These are real thoughts people have in secret in boardrooms when they go to do these kinds of research things. So that's what's going on with these errors. And next thing we want to do down below here is re-express alpha, beta, and power in terms of what I called conditional probabilities here. This is meant to be essentially a guide when we go into context and we have to say, using nothing but the context, what is type 1 error? You can come back to example 3 for a kind of structure to help out with that. But let's start by saying all of this happens because we're testing two hypotheses. H naught, mu equals mu naught against HA, mu not equal to mu naught. So this is the full alternative hypothesis, and this is just the specific alternative right up here. Let's start with alpha. Looking into the table, we can say alpha, this is the probability of concluding HA is true. And notice the wording I put in here. If we're going to write this out again in context, there's only two conclusions to a hypothesis test. We conclude that all alternative is true, or that we found evidence for it. Let's say it in that slightly better way, or we failed to find evidence for it. Let's say concluding we have evidence for HA. Saying we have evidence HA is true is okay as well, but we should say we found HA is true. We never are totally certain unless we took a census, in other words. And here's the big catch-all statement. So we rejected H naught, which means we concluded we have evidence for HA, but this is, let's say, given that, or under the assumption that H naught mu equals mu naught is actually true. So this is the conditional part. We only get that probability alpha to come out right if we add that extra conditional thing that happens, assuming the null hypothesis is true, which makes sense because that's how you conduct the hypothesis test in the first place. So that's what alpha is. Any questions at all, folks, coming up with the alpha? Okay, beta is way worse because when it comes to beta, you cannot use that right there. That's infinitely different betas that could come up with every choice of mu naught right here. In order to get beta calculated, we have to be informed by what the effect size is so that we can use this specific alternative right up here. So let's write this out really, really carefully for the next portion, beta. Beta equals the probability of, let's see here, a beta, we're on row 1, which means it's a probability of failing to conclude HA, let's say conclude we have evidence for HA. Now here's the tricky statement. The condition, the reason I called it a conditional probability is that this specific alternative is true. So we'll say, given that, or under the assumption that, let's go with that route. Under the assumption that the specific alternative HA mu equals mu A which would not be equal to mu naught, is actually true. And when we say actually true, we mean it's the literal truth of the population. Somehow, some way, the null hypothesis is actually true in this given information here. And for beta, we're saying that is literally the truth of the population, that one specific value we put in there is the correct value. So that's what beta computes altogether. And last thing is the thing we actually want, power. The good news is power is just a complement of beta. But before we write that down, any questions at all, folks, with any of these statements so far? Okay, so let's just write down the last one, power. I like that definition. It definitely sounds like it's important. The moment you name something to be power, so this is the power of the original hypothesis test, and it is equal to a real probability. It's the probability of correctly concluding we have evidence HA mu not equal to mu naught is true. So this is the entire alternative hypothesis statement right here, the one from right over here. But now we have to say, under the assumption, or given that, that specific alternative is also actually true. So it's right in this last statement. Assuming that, or given that, or under the assumption, let's go with assuming that, the specific alternative HA mu equals some value mu A informed by the effect size, which is again not the same as mu naught in the null hypothesis, is actually true in the population. So our goal is now to calculate power and also to clarify what's going on with alpha. The fact that power requires so much extra computation and thought, we have to change from the full alternative hypothesis to a very specific one just to get to beta and then power. And yet probability of type 1 error is specified at the start of the problem. That deserves some explanation as well. But this was our major goal in the middle of the notes, to take this table of type 1, type 2 errors, re-express it in a way that we can take this as a structure, translate it when we get into this context. We're going to do all of those things, compute the power of the test and other fun stuff under this assumption right here. And notice where it says, suppose that differences of a pH at a 0.3 are not considered to have practical significance. We are talking about an effect size here. Who knows how true that is, but biologists, ecologists would have to inform us on this. If we make that a statement, then the alternative hypothesis that mu is less than 5 becomes a specific alternative that mu is equal to 4.7. So that's how a specific alternative gets informed to information about the effect size. So we'll get into that problem and write down what we mean exactly by type 1, type 2 error, and all the other fun stuff actually compute some of these things like the power of the test. But before any of that, again, as promised, we need to justify why is alpha directly that probability. Any questions or comments first, folks, before we get into a closer look at alpha? Okay, well, these are both tricky values. Alpha is just tricky in the sense that it informs us on how to make the conclusion of the whole hypothesis test, and at the same exact time, enforces us on the probability of making a type 1 error. That's all kind of mysterious, unless we can really see it happening. So this is that problem right here. Because I called it a simulation, it's not meant to be something that we redo as a homework question or exam problem, but it's meant to really get at that issue with a type 1 error. So here's some random population. We're going to assume that sigma takes on a value of 2 to make the methods compatible with our notes. Well, suppose we have a simple random sample at size 30 from that population, perfectly distributed normally. And these are the hypotheses we'll test. Mu is 5, alternatively, mu is not 5. At the significance level, 0.05. Okay, so it says, using our syntax at the end of this page, demonstrate that the probability of a type 1 error actually is alpha. So let's give this a try. Here's the syntax. Let's just dump it into RStudio and let it sort all that out. But also compare with the information we have here to see how it comes together. Okay, so what this syntax is doing is first defining mu to be 6. So that means this null hypothesis is off by 1 unit. Mu naught is going to be set to 5. So that's the value that's in the null hypothesis, the value to be tested, or the hypothesized value. Sigma we set to 2, coming from this information. Sample size is set to 30. And the rest of it is how we're going to get these p-values. First thing I've done right here in this syntax is get a random sample at size n from a normal distribution with the parameter mu for the mean and 2 for the standard deviation sigma. Then this calculates our test statistic for the hypothesis test. This is a two-tailed test as we see here. So this is the same syntax we shared before for getting the p-value out. This gives me 1 p-value. And then next, we want 10,000 p-values altogether. So this is the remaining syntax. We just do a for loop to redo all that syntax a whole bunch more times. This statement here is telling us combine the old p-value p with a new p-value. So this 2p norm all the way up to f is just this part right here again. We just add a new p-value every single time we loop through here. Then this is just going to give us a histogram of all those p-values once we obtain them. So let's see what happens right here. Now notice, if the mean is 6, we're testing at 5, the null hypothesis is false, and we should reject it, right? We are expecting, hopefully, most of the p-values we would get are very, very small. So let's run it and see. Here's our p-values here to the right. Let me hide this so we can just focus on the graph. And it tells us if this is 0.1, almost all of the time, you're going to have a p-value that is in the rejection range, very, very small. The larger the sample gets, let's say it's 300 out of nowhere, the smaller your p-values get. Now they're all essentially less than the 0.1, and probably less than 0.05 as well. Let's drop that back down to 30. And to help us out a little bit more, let's compare again with what we wrote right here. Type 1 error alpha is the probability of rejecting the null hypothesis when the null hypothesis is true. It's not true down here, but let's make it more true. Go 5.5. Now, this is the value of the null hypothesis, mu naught. This is the true mean. And if we go from 5.5, this is the next graph. Notice what happened to the p-values. The distribution changed a lot. It's still heavily rate skewed. And, well, for probability alpha, we're not quite seeing that just yet. But let's suppose down here, if the significance level is at 0.05, we can now go make this even more true, maybe 5.7. Notice the distribution now this time. What would you say the shape is approaching as the value here gets closer and closer to the true mean? Sorry, say again. Not quite normal because of Yeah, still the right skew, but it is approaching something symmetric like the normal distribution. So you're on track with that part for sure. Anyone happen to know what distribution is symmetric but not normally distributed? That's kind of a weird question. Let's go 5.8 and see what happens next. Notice it changed even more. It's becoming symmetric, right? But it's flat symmetric is what we're approaching. We would say this is a uniform distribution at this point. And now let's just put in exactly 6. Now the null hypothesis right here is exactly true. I've changed the value 5 to a 6 this time. If it's a 6, and we run this whole thing, here's the shape we get this time. This is now the uniform distribution altogether. That's already pretty weird. P-values want to behave in a way that they're always really small, the more false that null hypothesis is. So even if I go 5.9, run this whole thing again, still pretty flat, right? And the difference between 6 and 5.9, it might be so small as to be totally negligible, below the effect size, in other words. But if you make your sample size large enough, you can detect even a small, for practical purposes, insignificant difference because your p-values get smaller and smaller again. So we can detect this small difference with a large enough sample size. But let's go back to this picture. Make the null hypothesis exactly true, we get this distribution out. And the distribution goes from 0 to 1. I have a frequency here, but if I made it a density, it would go from 0 to positive 1. Let's capture this in as a density graph next. So I'm going to change my axis a little bit. Well, let's go like this. So here's all of our p-values. The density is just saying how many times, or excuse me, the frequency is just saying how many times we were in this region. Looks like about, hang on, maybe 1,000 times. But if we view this as a density graph, here's what it would look like. Let me call this density, go from 0 to 1. Now, if we model the heights of these rectangles, you'd use a flat curve, and that would be the uniform distribution. Area under this curve has to be exactly 1 for it to be a legitimate probability model. That's why we're viewing it as a density curve. And now, next thing we can add here is this tick mark. This tick mark is right at 0.05, which is equal to alpha. So we can draw a vertical line segment going up this way. And we want to consider this area right here. So this is kind of interesting in a way. If we force the null hypothesis to be exactly true, which is what we did in our simulation here, then the p-value, because of the flat uniform distribution, is really anywhere. It's totally random. It doesn't favor any location whatsoever anymore. It's as if your p-values are basically useless now. But there's a chance it ends up right here. And that chance is exactly the area of this strip. That area is going to be equal to 1 times 0.05, which is 0.05, which is equal to alpha. So if alpha has a 5% chance of being in this region below 0.05, it means we have a 5% chance of rejecting the null hypothesis as a type 1 error and concluding this is true when it's just patently false now. So that's how the probability of a type 1 error becomes exactly alpha. It's only because when we say probability of type 1 error, we include this, that the null hypothesis is the actual truth of the population, flattens out all your p-values when you make that assumption, and so you have a 5% chance of being in this rejection region below 0.05. So that's the full story of what's going on with the type 1 error. How do folks feel about that? Is it kind of confusing and vague, or does it kind of make sense seeing it this way? from my point of view on this, I think it's really kind of vague, especially seeing it the first time. The bigger takeaway is if you make this completely true, that curve is totally flat. And that means your p-value can be anywhere. It doesn't favor a location. And that's what's giving us a 5% chance because we set it at 5% and being in the rejection region. We set it to a 10% chance. This moves over to that location and the area is now 10% of the total area. So conditional probabilities are weird. That's part of what makes alpha kind of tricky. What we did, folks, this is the discussion of why is the probability of a type 1 error literally just alpha? Next things we want to compute is the power of a test. We'll do it in context like we mentioned on the next problem below. So let's maybe move this up a little bit. Here's that next problem. We're told to start this off, emission of sulfur dioxide, SO2, by industry set off chemical changes in the atmosphere that resulted in acid rain. I grew up in the 80s, so we heard about this all the time. We talked about how the Lincoln Memorial was starting to crumble, that kind of stuff. Good information here is that distilled water is neutral at pH 7. Lower values indicate acidity, and black coffee is a pH of 5. So pretty acidic relative to distilled water. All this is context so far, but it looks like it's all about sulfur dioxide in the atmosphere. We're told next, suppose pH measurements of rainfall on different days in a Canadian forest follow a normal distribution. That's a humongous assumption, but let's roll with that right there. We have a standard deviation at 0.5 for the population. That's a bigger assumption in my opinion. And we're going to plan to test these hypotheses. This might be a study that's funded by the Canadian government because we're in Canada, or it could be a study that has been pioneered by maybe some industry, some corporations inside Canada or outside. So we're going to test the null hypothesis that mu is 5. Let's write in really quick here, what do we mean by mu? It never directly defined the parameter, but it is implied here. pH measurements of rainfall on different days in a Canadian forest. Let's say mu equals population mean pH of rainfall in this Canadian forest. So we've got the parameter down, and the null hypothesis that, yeah, there's lots of SO2 in the atmosphere in that forest. We're saying mu is 5, so an acidic pH. Well, that's the value we're testing at acidic. And the alternative hypothesis is saying it's actually more acidic than that assumption even right there. So we're going to say in the alternative, acid rain is a bigger problem than what was even indicated here potentially through the context. And there are two objects, or I shouldn't say objects, there are two groups with interests in this context of a Canadian forest. Let me put a T in there. There we go. There's the industry. An important group of individuals, they control a lot of money in Canada. And if industry suffers, so do the ordinary Canadians in a roundabout way. It'll take some time. But there's also the ordinary Canadian citizens themselves who are probably concerned about their Canadian forest and the effects if this is actually true. So when we go to formulate this 5% significance level, we have to make a balance between what is a type 1 error and what is a type 2 error, and essentially, who are we going to upset, piss off the most? Who could we be sued the most? Who are we most liable to? If, for example, we reject the null hypothesis, conclude the alternative hypothesis is true, the industry in Canada is going to potentially suffer because there could be real legal action that comes down the line. And that's a major problem if we had chosen this with no thought. They could come back after the people who did the study and look for any ways we were unethical. So selecting this value right here is absolutely critical, and some thought has to be given there. If we can never justify, we planned this, and we accounted for what could happen, and we selected this error, or excuse me, this level of significance, then we could really be in hot water here. So let's write this out. A type 1 error, just to see what it looks like, and a type 2 error as well. Well, when you're first doing this, if you remember it's a two-way table, it's sometimes a really good idea to have this kind of guide right here. And this is good to look at as well. It can help us write these things out. I'll leave the thing that we wrote out in the bottom more for your reference when you're doing this as a homework problem or studying for exams. And just to help out with the notes, let's solve both of these by viewing the table right here just as a guide. It's a two-way table, so there's more information than it looks like when you consider these. So practical interpretation of type 1 error, and this is the hardest part about it, we have to use the given context as well. Because it's a practical interpretation, we're not writing down symbols, we're saying what things are just using ordinary words. I think we have enough time to give type 1, type 2 error verbally. So let's say first, what do we do in a type 1 error? We reject H naught. We don't want to say that though, we want to say, what is your conclusion? Your conclusion is you found evidence that that part's true. So we'll begin by saying, the study found significant statistical evidence that we can just read out the statement here by looking up what the parameter mu was, that the population mean pH of rainfall, and I'll say just in this forest, it's implied we're in Canada for this whole problem. So I'll say in this forest is less than 5, and that's a comma right there. Anytime we're reading out type 1 error, type 2 error, we always say the extra condition. I'll say here, given that, back up here, that true mean, well, let's say that population mean, given that the population mean is actually a pH of 5. So we made a really strong conclusion in a type 1 error. Mu is less than 5. These conclusions have action sometimes, so lots of things could happen in Canada. And we made that conclusion as a mistake. We were really at 5, which may not have been a big of a concern. At 5, the reason that hypothesis was set this way, that might have been at the cutoff where no action happens unless we found evidence that this is true. So that's what happens in a type 1 error. Now we'll turn it around into type 2 error next. Any questions first at the moment? Okay, let's write this in. Type 2. So first we want to say, what did we do in a type 2 error? What's our conclusion? We failed to reject H naught, which still means we go back up here. This is kind of weird. This is the comment that we made at the very start of class. And we almost read out this statement, except we just put in between here, the study failed. Oh, didn't mean to throw that, sorry. The study failed to find that's this significant statistical evidence. So let's read out. The study failed to find significant statistical evidence that, come back up here and just read it out again, the population mean rainfall is less than a pH of 5. Okay, so that's just this part. We failed to reject H naught. The thing we actually say in our conclusion is we failed to support the alternative hypothesis, failed to find that evidence that's less than 5. And then the big statement is, given that, a specific alternative hypothesis let's say this in a slightly nicer way. I'm trying to write out a practical interpretation. So let me say, given that the population mean is actually well, we could say less than 5. That would be a valid way to write this out. But it doesn't seem to be in the spirit of this table, right? Because we kept harping on the specific alternative. So in your homework, if you just said, given that the true mean is actually less than 5, that's actually appropriate and that would be okay. If you want to be a little bit more descriptive, read on in the problem where it says differences smaller than a 0.3 are not considered to be important to have practical significance. We want this test that will almost always reject the null when the true mean is 4.7. The 0.3 is the effect size. The 4.7 is the specific alternative. Well, let's go with that route because it ties together things in the table a little bit better. Given that the population mean is actually a pH of 4.7. And let me just say here in parentheses, HA mu equals 4.7 is the specific alternative, which will enable us to actually calculate the probability of a type 2 error beta, which gets us to our ultimate objective, calculating the power of the test. So there it is, folks. Let's actually just leave the table there. Why not? It causes no harm. We have type 1 error, type 2 error, and we have a couple minutes to think about this. In your opinion, there's no wrong answer to this one. Just defend your answer and you're totally fine. So if this comes up as an exam question, it really is an opinion answer. So in your opinion, looks like we're talking about industry in Canada, probably because if this study makes an error, that's who we are more liable to. They have the best power to come back at us. So in your opinion, which one is more damaging or concerning to industry in Canada, type 1 or type 2? Any volunteers to say which is worse? Why it goes there? Yeah, go ahead.
Maybe type 1 because it's not quite as specific, whereas with type 2, it's a little more specific. It can be more easily interpreted, whereas if you put out a study that has this kind of vague interpretation, then that might cause panic. And if it's publicly traded, that could potentially cause a class action lawsuit, which could potentially cause shareholder shares to fall in the stock market.
Yeah, shareholder panic at that point.
It depends also, though, it might depend on the industry. Since if it's producing, it's probably something manufacturing, so.
Yeah, absolutely.
If there's some sort of pollution that they are considered responsible for according to a study, then that could potentially, the industry itself might not have as much, might be at risk of being shut down by government and it would, which again, the shareholders, but also that could have a substantial economic cost because, if it's manufacturing, they're hiring people, probably pretty good jobs. And that could.
Yeah, for sure.
Uh,
Chemists and all
and if
sorts of
it's
people.
An area that's a more rural area or industrial area that could cause substantial irreparable harm.
I agree with you. Yeah. So in my opinion, and sounds like what you're saying as well, type 1 error is damaging to industry. Because if we make the conclusion the alternative hypothesis is true, and it isn't even true, we're needlessly punishing industry, which is the detriment to all people, like you're mentioning, shareholders, the workers, the entire Canada economy could suffer over this. Looks like that's the bigger danger. But in a type 2 error, we fail to show that's true, which means probably no action's being taken. But that's going to piss off the ordinary citizens the most if type 2 error happens, right? Because we failed to make that conclusion, which means nothing's going to change in the industry, no new benchmarks or things that they have to abide by. And so whatever damage is going on can continue to do so. But yes, I agree with you. If we're focusing on industry in Canada, type 1 error is the absolute worst. So that's the one to avoid. Well, we'll come back to that and write down those results a little bit better, but it's always good to think about these things. There's often two groups of people you have to consider in a hypothesis test, and you pick your significance level alpha to compromise between pissing off one or the other. You might piss off one for sure if you make an error. But this is a good stopping point for us. Any last questions at all, folks, before we call tonight? Okay, we'll wrap this one up when we come back next class. And then looks like we're also going to be finally launching into chapter 17. But have a great night, folks. I'll talk to you all on, let's see, Thursday's class.